graph and then state the domain and range. So when you're going to sketch the graph, just put it in your calculator. Here we go. Go to y equals, I already forgot what it was. 1/2. Okay, got it. 1/2. 3 to the x. Does that look right? Yours will probably have up arrow x. Does that look right? Now if you just hit graph, that may not tell you much. You go to the table and plot the points. Yikes. I don't want to start at 107. Let me start at 1. So put a point at 1, 1.5. Put a point at 0.5. Put a point at 2, 4.5. And then you see what's happening as we go toward the negatives. It's getting closer and closer to 0, but never crossing. So it looks something like this. 1.5, right, was up here. So it looks something like that. And so your domain is left-right. This is going to continue to go out to the right. So your domain is all real numbers. And we see it's going to go pretty obviously going to the left. Your range is going to be your y values, and we don't use all our y values. We only use everything from here up, because it'll never get below the x-axis. So we'll say the y values are all greater than 0. 90% of the ones you do in domain and range is going to be just like that. Domain is going to be all real numbers. Range is going to be y greater than 0. Now they might trick you with a greater than or equal to. They might trick you with less than. So make sure it's the greater than, strictly greater than symbol for the range. Number 2, determine whether this function is growth or decay. So 2 ways to tell. If this number in parentheses is less than 1, it's going to be decay. If you forget that, you can put it in the calculator. Somebody tell me what it is again. I forgot. 0.8 something. 2/3 to the x. You hit graph. We watch the graph go down, 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 down. Okay? So it's not going to go negative. It's kind of like, you know, if you have a petri dish of bacteria and they start decreasing in number, maybe there's half as many now as there was an hour ago, and there's half as many in an hour as there is now. Well, it's going to get half and half and half and half, but you'll never get negative numbers of bacteria in the petri dish. It'll just get closer and closer to being 0. You tear your paper in half and keep tearing it in half and keep tearing it in half. How many times can you tear it in half? Hypothetically, it would be infinite. But you'd have to get down to very, very microscopic stuff. But you never get a negative amount of paper. You never get a negative amount. You just keep getting less and less and less, but not into the negatives. So this is going to be a decay situation. Two reasons. Because that is less than 1, and because the graph does this. Number 3, write an exponential function whose graph passes through 0, -6, and -2, -54. So the form for exponential functions is y equals a times b to the x. A is kind of like our y-intercept. So this is going to give me a clue, and I'll put that in for A. So I know part of the equation is going to be y equals -6. I don't know what B is, but whatever it is, I'm going to take it to the x power. In order to find B, I have to come over here and use this point. I'll put the -54 in for y, the -2 in for x, so it'll look like -54 equals -6 times this B that I'm looking for to the -2 power. And I need to solve for B. So first thing I'll do is divide both sides by -6. Okay, and I get a positive. -54 divided by -6 will be a positive 9. So at this point, there's a couple different ways to go about it. The easiest way for me to see it, visualize it, is to go back to something that I do a lot, well, relatively a lot, and that is when I have a negative exponent, I take it to the denominator. So it's 1 over b squared. And I can, at this point, well, now or later, it doesn't matter. Let's go ahead and do it now. I want to go ahead and get b out of the denominator. So I'm going to multiply both sides by b squared. That cancels there, and I'm left with b squared times 9, or 9b squared, equal to 0. Oh, 1, sorry, 1. Not 0, I didn't subtract that divided. Now I'm going to divide off the 9. And so basically what happens is the b squared and the 9 could switch places. The 9 can go in the denominator, the b squared can come out here. But just to show the algebra that you have to do to make that happen, b squared is now 1/9. Take the square root of both sides, and b would be 1/3. So that's not really my answer. I need to really box that in. I'll come up here and write 1/3 to finish out the equation. Not all of them will be that complicated where you have a negative exponent and a negative x value here. That kind of messes things a little, makes things a little bit more complicated. Where you have the variable you're looking for in the denominator, that always makes it a little bit tricky. So it's supposed to be a 2x plus 2. So what we need to do is to get like bases. So 243, I don't think 9 to any exponent is 243. It's 9 squared.
9 times 27.
Okay, 9 times 27. And 27.
47 divided by 9 would be 3.
So we know it's going to be divisible by 3, or it's going to be a power of 3. Let's just go with 3s. 3 to the what? 5th? Okay. Let's go back. This is 3 to the 5th. With the 2x plus 2. 9 is 3 squared to the 4x plus 4. Now I need to multiply these two exponents together. It's going to take some distribution. It will be 3 to the 8x plus 8 equals 3 to the 10x plus 10. But the good thing is I have the same base, so they can drop out. And then I can start to solve for x. So let's subtract 10x from both sides. And I get -2x. And then I'll also subtract 8 from both sides. I'll get 2. So then dividing by -2 gives me an x value of -1. Any idea what we're going to do with that? Close. 6 to the 1/6 is not equal to 6.
Yeah, you gotta multiply. Some of that nature.
You got to take the exponent and make it, see this is 6 to the positive 1 power, -1. 1/6 is the same as 6 to the -1. So then if that's equal to 6 to the n plus 4, I have the same base, I can drop the bases. -1 is equal to n plus 4. Subtract 4, n is -5. And it goes that quick once you see that 1/6 is equal to 6 to the -1. (32 to the x less than 16 to the x plus 2). We need to get like bases again. What will be our base? 2. Very good, 2. So 2 to the what gives me 32? 2 to the 5th? So you may have to use your calculator to figure that out. 2 to the 5th to the x is less than, and 16 is 2 to the what? 2 to the 4th to the x plus 2. So then we multiply our exponents together. 2 to the 5x is less than 2 to the 4x plus 8. Bases are the same, so 5x is less than 4x plus 8. Subtract 4x, and it's one step and done. X less than 8. Number 7, we're only asked to write this in exponential form. So this is logarithmic form. This is our base. This is our exponent, -1/2. And the question now becomes the answer. And that's all you have to do. Now, is this true? Well, 81 to the -1/2 is 1 over 81 to the positive 1/2. And a half exponent means square root. The square root of 81 is 9. So it is true. Not all of them are. And sometimes you may have a true or false. All right, number 8. Evaluate log base 9 of 97. Now there are a couple different ways to do this. Now that we know how to convert them to common logs, the easiest way is to take the log of 97 over the log of 9, and we put that, since it's a base 10, in our calculator and get the decimal.
Need it?
I'm going to go ahead and show it, maybe. It's a log of 97. Nope, not natural log. Close parentheses, don't forget to do that. What's the denominator, 9? .0820. 4 won't round it to 0 up. Bad memory. 0820. Number 9, we could do the same way, but I want to show a different method also. If you set that equal to x, and we're looking for x, then 4 to the x power is equal to 128. If we change it into exponential form. 128 is the same as 2 to the 6th. Seven. 2 to the 7th. Okay? So that means if this is 2 to the 7th, and 4 to the x is the same as 2 to the 2x, then 2x is equal to 7, and x is 3.5. Your calculator would do the same thing if you did log of 128 divided by log of 4. But in case you're stuck in the wilderness without a calculator, you can still do your logarithm. It's in logarithmic form. So if we change it to exponential form, then 36 to the 3/2 is equal to n. Now you can actually put that in the calculator. Just make sure you put the exponent in parentheses. But it could be simplified by hand too, because this would translate in radical form to the square root of 36 to the 3rd. And 36 to the 3rd is 6 squared. So this is the same as 6 to the 6th. 36 is 6 squared. 6 squared to the 3rd is 6 to the 6th. And then if I go back into exponential form, put it like this, that would be 6 to the 6 over 2. 6 over 2 reduces to 3. 6 to the 3rd, crap, I still need my calculator. 36 times 6, I guess I can do that. But simplest way, you make sure you don't run out of time, is put 36 to the 3 over 2 in your calculator. What did I do? 36, up arrow, parentheses, 3 divided by 2, which should be the same as 6 to the 3rd. Cross my fingers. Good. So what we see on number 11 is we have log base 5 of something greater than log base 5 of something. And if that's all we have is a log of something greater than a log of something, then we can set the somethings equal to each other and drop the logs off. 8x would be greater than 3x plus 10. Now, if there had been something else there, you have to make sure that there's no coefficient in front of the logs. You have to make sure there's no plus anything outside of what it's taking the log of. But once you get there, you just subtract 3x from both sides. Divide both sides by 5. And you're done. On problems like number 12, where they tell you to use these numbers, then you need to show the steps that you're doing using these numbers. You can put it in the calculator to check your work, but it wants you to use, somehow, simplify it through the use of those. So 48 is, we break down 48. 48 is 2 and 24. which is 2 and 2 and 12, or 2 and 2 and 2 and 6, and finally 2, 2, 2, 2, and 3. So it's 2 to the 4th times 3. So if I rewrite this as log base 5 of 2 to the 4th times 3. And then I break this up into a double log of addition. Log base 5 of 2 to the 4th plus log base 5 of 3. The 4 can come out front. Log base 5 of 2 is 0.4307. Log base 5 of 3 is 0.6826. And you put that in your calculator and get the answer. You get 2.4054, which should be the same as if we did log of 48 divided by log of 5. Well, a little bit. So there's a rounding situation that occurred somewhere with these numbers. So if both of those were rounded up, then it would throw off our answer a little bit. Because that would stay at 0.4053. What can we do with number 13? You could change it to subtraction. To change it to subtraction, so it'd be log base 5 of 5 minus log base 5 of 3. 1. Very good. Recognize what that is. Just 1. And then what was that number? What you get should be your answer. So 3174.
I just did 1 minus the log of 3, and I got.
Well, it's not the log of 3. It's a log base 5 of 3.
Oh, log base 5 of 3. I thought that said logs or something.
Now, what you could do is to follow the same shortcut we did on 13, but you got to make sure you do your notation right. Log of 5/3 divided by log of 5. If we did a base 10 on those, we should still get something pretty close.
Wait, so you divide the top number by the bottom?
14. Any ideas? What would be my first step? And what are some things we have to deal with? We have to deal with those things in front of the log. We also have to deal with this plus sign. Because ideally, we would like for it to be a log base 4 of something equal to a log base 4 of something else. Drop off the logs and let the somethings equal each other. And then we go back to algebra 1. Not yet. Only if it's just log of something equal to log of something. No, none of this stuff. No double logs. You can't have two on the same side. It's got to be just one on the left and one on the right. So here's what we can do. We can take the 1/4 and make it an exponent, take the 1/2 and make it an exponent. And a 1/4 as an exponent on 81 is the same thing, and you can put that in your calculator like that, is the same thing as the 4th root of 81. 3 times 3 is 9, 3 times 9 is 27, 3 times 27, I hope, is 81. So if 81 is the same as 3 to the 4th, and I want the 4th root of 3 to the 4th, well, that's just 3. So this becomes log base 4 of just 3. So if 81 to the 1/4 is the 4th root of 81, what do you think 25 to the 1/2 is? Oh, sleep. Square root of 25, 25 is 5 squared, square root of 5 squared is 5. So we end up with plus log 5. Still equal to log base 4 of n. Now if we have a double log, a log base 4 of 3 plus a log base 4 of 5, then we can make it a single log by multiplying the 3 and the 5. Now we have it. Log base 4 of something equal to log base 4 of something. The logs cancel, the somethings are equal to each other, and I don't even have to do any algebra. What about 15? Okay, so on number 15, it's similar, except we have subtraction. We don't have any coefficients out front to deal with, but we have subtraction. And so what do we do with a double log of subtraction? We divide. It would be a log base 2 of 2x plus 6 over x. That divided by that. Still equal to 3. Now we don't have a log of both sides, so what are we going to do? How can we get rid of the log command or the log notation? We change it to what? What's the inverse of log formation? Exponential. So we take the base to the 3rd power equals, and the question becomes the answer. So 2 to the 3rd equals 2x plus 6 over x. 2 to the 3rd is 8. Multiply both sides by x. 8x equals to 2x plus 6. And now I'm in a place I've been before. A little more comfortable. 6x equals 6. X equals 1. just to go back over, we had addition. Any ideas on 17? What do we do if we have a exponent in the variable? What can we change it to? It'd be nice if 50 was 6 to the something power, but it's not. What can I do? Let's do that. Just log base 6 of 50 equals to n minus 2. This was what you should have been doing on, I believe, 7-7. Maybe some of 7-6. This we can put in the calculator as log of 50 over log of 6. And then if we add 2 to that result, we get n. So log of 50 divided by log of 6, get an answer, and add 2. Log of 50 divided by log of 6, get an answer, add 2, 4.1833. You get log of 2 to the y equal to log of 5 to the y minus 2. Those exponents can now be brought out front. So we end up with y times log of 2 and we're going to skip 18, but just so real quickly I'm going to go through it. What we would have to do is distribute the log 5, and so we get a y log 5 minus 2 log 5, and then we would subtract the y log 5 from both sides, so we get y log of 2 minus y log of 5, and then equal to a negative 2 log of 5. We can factor out the y here, and we get log of 2 minus log of 5 equal to negative 2 log of 5, and then we just divide both sides by log 2 minus log 5, and this we have to somehow get in our calculator because those cancel, and we're left with y equals all of that. And so that's why we're going to skip it. Number 19, we take the log of both sides. So the log of 4 to the 3x plus 1 be less than the log of 28. We can take this exponent, can now become a coefficient on the log of 4. So we get 3x plus 1 times log of 4, which is less than log of 28. Divide both sides by log of 4. Is 3x plus 1 greater than, less than log of 28 over log of 4. Add 1, no, subtract 1, divide by 3. That'll cancel the 1s, that'll cancel the 3s. We're left with x less than log of 28 over log of 4 minus 1 divided by 3. 58. That result, -1 divided by 3. 1 divided by 3.467. That 8 will turn into a 9. That guy right there needs to make that a 9, so 0.4679. 0.4679. Number 20 wants us to express log base 12 of 4 in common logs and then approximate to the nearest 10,000. So the change of base formula would be, write this as log of 4 divided by log of 12. And then to approximate to the 10,000s, we have the log of 4 divided by log of 12. Sure that's right. 0.57788. So that means I need to make that a 9. 0.57557. Number 21, suppose you deposit $3,000 into account paying 2% annual interest, compounded continuously. Use the formula A equals P times E to the RT power to find the balance after 5 years. A is going to be the amount after 5 years. P is the principal, the amount we're originally depositing. E is just old E. Rate is 2%, which we'll write as 0.02. And then the time is going to be 5 years. So we can put that in our calculator. We'll put 3,000 times E to the 0.10 power, because 5 times 0.2 is 0.02. So 3,000 E to the 0.1. $3,315.51. That'll be our balance after 5 years. Well, number 22, we're into natural logs now. If you change this into exponential form, it might be easier just to relearn this as log, natural log, ln is the same thing as log base e. So x minus 5 equal to 3 would be translated to e to the third equal to x minus 5. So if we want the value of x, we're just going to add 5 to both sides. We can put e to the third in our calculator. E to the third plus 5 will be equal to the value of x we want. Third plus 5. 45.0855. The value of x. Same thing with number 23. But we have an inequality we have to deal with. And so you could say, change it into logarithmic and say log base e of 9, but what happens here is that would need to reverse the inequality to be equal to negative 4x. So what might be easier, and you could put this in your calculator, but the problem is we might get that backwards. 4x should actually stay on the left. The other way to do it is to take the natural log of both sides. And when we do that, we move the exponent of negative 4x out as a coefficient times the natural log of e is less than or equal to the natural log of 9, and the natural log of e is equal to 1. So then I have negative 4x times 1, just negative 4x, less than or equal to natural log of 9. Divide both sides by negative 4. And I do have to reverse the inequality still. Greater than or equal to, and let's put that in our calculator, natural log of 9 divided by negative 4. Natural log of 9 divided by negative 4. Negative 0.5493. For number 24, we're going to need to use the formulas from 7-8, the exponential growth and exponential decay formulas. We've got to decide if this is a growth or a decay. After 12 hours, half remains. Okay, half of it remains. So that means it's a decay. So that means we need to use f of x equal to a times e to the negative kt power formula. Now, half of a 16-gram sample remains. So how much is left? 8. Started out as 16. E to the negative k, we don't know. T is our time, and this happened over a period of 12 hours. And so with all of this information, we should be able to figure out what the constant is for the rate of decay for this radioactive element. So we would first divide both sides by 16. I get a half, 0.5 equals E to the negative K times 12. If I take the natural log of both sides, the natural log of 0.5 would be equal to the natural log of E to the negative K times 12 power. And I'm going to write that as negative 12K. Then I can take that exponent and make it a coefficient. So the natural log of 0.5 is equal to negative 12K times the natural log of E. Well, the natural log of E is 1. So I don't need that anymore. Divide by negative 12. And this value right here, once I put it in the calculator, would be equal to k. Natural log of 0.5 divided by -12. Divided by -12. 0.05776 would be 0.0578 to the 10,000ths place. 0.0578. Number 25, a savings account deposit of $150 is going to earn 6.5% interest. After how many years will the investment be worth $450? Use y equals a times 1 plus r to the t and round to the 10th. So y is going to be the amount at the end, which we want to be $450. We're only going to put in 150, so that's our original amount. The rate is not going to change. It's be 6.5%, which is 0.065. We need to know how long that's going to take. So we're going to solve for t. So this becomes, divide both sides by 150. 450 divided by 150 is 3. 1 plus 0.065 is 1.065 to the t power. Now I can turn this into logarithmic. Okay, so I have a log of base 1.065 of 3 equal to t. We can do it that way, but let's take a different approach, since I don't want to have a base of 1.065. If I take the natural log, or the common log of both sides, so the log of 3 will be equal to log of 1.065 to the t power. The t becomes the coefficient, so I get log of 3 equal to log of 1.065 with t in front. So if I divide both sides by log of 1.065, then I get the value of t equal to log of 3 divided by log of 1.065. So again, log of 3 divided by log of 1.065. Log of 3 divided by log 1.065. I get 17.445. I'm just going to call it 17.4. 17.4 what? That's t. 17.4 years. Let's leave in there 17.4 years for it to triple in value. All right. The other way that I was going to do it would give me the same result and actually turn into the same steps in the calculator. If I change this to exponential and make it log base 1.065 of 3 equal to t, then if I do the change of base formula, that is log of the logarithm divided by log of the base 1.065. Changing both the common logs. And I end up having exactly the same thing in my calculator that I did before. Log of 3 divided by log of 1.065, which is 17.445268.